Good afternoon or evening or morning, everyone. I'm here to welcome you to our first webinar. I'm just going to hold on for a few minutes just to see if anybody else joins. So I'm just going to mute myself and we'll start in a couple of minutes. Okay, thanks. Okay, so it's 6:02 here in Colorado. We've had a few more people join, so I think we'll get started. I'll say it again, good afternoon, evening, or good morning to those of you who've just joined. Welcome to our webinar. Thank you for joining us. I'd like to welcome you to Sputtering Components' first webinar. Being the first webinar for us, we hope it runs smoothly, but you never know, so I apologize for any technical difficulties we might experience. We were successful this morning, so hopefully we'll have the same luck again this afternoon. It's great to see all of you joining us today, and I hope everyone's doing well during this challenging time. In today's 30 minutes, it'll be approximately 25 minutes, 30 minutes webinar. We'll discuss our dual magnetron plasma treatment source, or DMPTS for short, and we'll also introduce our new CCM block that we've added to our internal mount end block range. This DMPTS talk, that part of it was originally scheduled for the Vendors Innovation Showcase session at the SVC conference in Chicago this year that was unfortunately cancelled with everything going on. So I'm happy to have the opportunity to be able to present it to you today and have a little more time to show you some additional data. If you have any questions throughout the presentation, feel free to ask them. There's a Q&A box at the bottom of your screen, and you can put the question in there, and I hope to be able to get to answer them at the end of the presentation. If I don't get to your question, I'll follow up in the next couple of days. And if you have a question that you'd prefer to ask offline, feel free to send me an email. My contact information will be at the end of the presentation if you don't have it already. There are also some links for additional information available to you in the resource box on the screen. So feel free to check those out. We've got the data sheets for the DMPTS and the CCM block. And there'll be a survey at the end of the webinar, so please stick around and let us know what you thought for our first go. It'll pop up automatically at the end of the presentation, or you can click the survey at the bottom of the screen. So the webinar will be recorded and also available on demand within 24 hours, so it will get sent out to you shortly after, and you'll receive an email with the link to the webinar. So I'd like to introduce myself. Most of you know my name is Sarah Williams. I've been with Sputtering Components for almost 8.5 years. I've been the Senior Applications Engineer for the past 1.5 years or so, and was Sales Manager for North America prior to that. So, okay, let's get started. So as I said, the first part of the talk will be on the DMPTS, also called the Envision. Here's the outline of the talk. We'll look through the applications, the markets, alternative technologies and their limitations. We'll go through the design of the source and the theory of operation, and I'll present to you some test data for surface energy and adhesion, and then look at the conclusions. And then after that, we'll move on to just introducing briefly the CCM block. So the main applications for the DMPTS are in pre-treatment of polymer-based substrates prior to vacuum deposition. We have done some work on glass also, but the main bulk of the work has been on plastics, either rigid 2D substrates, you can see the picture in the bottom left, or plastic film, roll-to-roll, web coating, there's a roll of film there in the middle picture, or rigid 3D substrates such as car headlamp reflectors. We'll go through the markets for these substrates here. So for rigid 2D substrates, glass replacement windows such as automotive, safety or privacy screens, flat panel displays, OLEDs, organic solar cells, solar control, decorative and optics. They're all the applications that you might see for 2D substrates. For plastic film and roll-to-roll and web coating, solar control coatings, low-E films, OLEDs again, capacitors and thin film batteries of interest these days, and flexible circuit boards, electronics, security inks, metal flake paints, packaging materials, and another interesting application for fabrics and textiles. When we look at rigid 3D substrates, such as automotive applications, car headlamps, you saw the picture on the other slide, and then other metal-coated plastic parts that you might find in a car, consumer electronics housing, such as on your phone, EMI shielding, and also decorative coatings. So there are several competing or alternative technologies to the DMPTS. These are ion sources. There are 3 different types of ion sources. You can see one of them from Vico on the right, the top picture there, either anode layer sources, end hall sources, or gridded RFDC. Also glow discharge and magnetron plasmas. The picture in the middle there from Genco is from a rotary magnetron plasma. You can also use to treat a substrate, either standard or inverted magnetrons. Plasma sources, RF, MF, DC, and hollow cathode sources, such as the picture at the bottom from Isoflux. So these are all alternative technologies, but they do have limitations, and we'll look through those now on this next slide. The main limitation really is in substrate damage with overtreatment due to higher energies, and I'll show you a slide soon for the ion energies of this source versus competing technologies. The ion energies are typically much higher, and you can get substrate damage. There's also a limited process pressure range, especially with microwave plasmas. The pressure is usually too high for process stability. They have a short component lifetime. You have to change out the electrodes much more often, whereas we use a titanium electrode, and you'll see that in the design in the next slides too. They can also be a substantial source of contamination due to target erosion. You don't really want to have that contamination in your film when you're just trying to treat it. Glow discharge in particular produces particles and can be a pretty dirty process, so we also want to avoid that. And the DMPTS is a very clean operating plasma treatment source. Also, often these sources are unsuitable for large area, and you might need multiple sources and power supplies to achieve acceptable treatment. So that can also get expensive and complicated. For magnetron sputtering, when you're trying to treat it by using a magnetron, you can often not effectively treat the substrate with the plasma before a film begins to grow on the surface. And obviously the whole point is to treat it before you're growing a film. And the designs are usually much more complex too. So here we'll look at the design. It's a stacked magnetron design. You'll see in the next few slides the electrodes on top of each other. It operates off medium frequency AC or bipolar DC power, such as a advanced energy PE2 supply, something like that. It can be compatible with adjacent processes. So in the same system, if you want to have the treatment and sputtering, planar, rotary, other methods, this can be in the same chamber because it will operate at the same pressure. I mentioned the electrode life. We have a long electrode life with the titanium electrodes. The targets can be changed very quickly, so it's very easy to maintain. And it can be mounted, like many of our products, our M blocks, either M block mounted, cantilever mounted, or one big advantage, it can be remotely mounted in the chamber, so it can be positioned anywhere in the system, and you basically would have an umbilical to take the services to atmosphere. A typical operating power is around 2 to 4 kilowatts per meter. the maximum power is around 5 kilowatts per meter. You'll see some slides later, we did use 7 kilowatts, and you could use higher powers if you're doing a short duty cycle, but it's best to be around these lower powers if you're doing long cycles. The operating pressure is 1 to 40 millitorr, and we've seen the best operation really at between 1 and 5 millitorr. Then I'll present some of the surface energy results, but you can see that we can get a greater than 65 dynes for surface energy to help with adhesion, and that's running at 6.7 meters per minute. So we'll look here at the design advantages. I mentioned it's a simple design, a robust design. There are no moving parts. There are no high precision consumable parts. The titanium electrodes have an extremely slow sputter rate. So you could go for 200 hours plus in, before having to change, actually probably much longer than that, before having to change out the electrodes. It has extremely low contamination rates, I've mentioned already, and long periods between replacement. And all the parts that are exposed to the plasma and the substrate are designed to be sandblasted for easy cleaning. So it's very easy to maintain. We'll look here at a cross-section, and you see the stacked electrodes here. You've got electrode A at the top, electrode B at the bottom. Then there's fasteners holding those electrodes in there. At the bottom there's a gas manifold where you would introduce your reactive gas, oxygen, nitrogen, together with the argon. And then the source opening at the top there. And of course you connected the electrodes to the power supply. So we'll look at the theory of operation of the plasma production. There are 3 stages: electron generation, process gas ionization activation, and plasma expansion. So you can see those 3 stages there. And on the next 3 slides, we'll just look at the details of those a little bit more. So in stage 1 for electron generation, there's alternating sputtering between the 2 low sputter yield electrodes with high secondary electron emission. And that creates the low impedance plasma cloud that you can see, this sort of grey cloud here. And the substrate is below, so the plasma will expand out to hit that substrate. And this can be either a static substrate or a moving substrate. In stage 2, the process gas ionization activation, the process gases that I mentioned already, oxygen, argon, nitrogen, are introduced through that manifold that I talked about directly into the plasma through the back wall of the source. So that then mixes into that cavity. And finally, for the plasma expansion, so the ionized or activated process gases combine with the electrode secondary electron emissions to increase that plasma density in the cavity until it's forced to expand out of that opening. And then we also have low strength magnetic fields to produce this collimated beam of plasma. And we typically see that we can have a source to substrate distance up to 200 millimeters to get effective treatment. This is a nice slide from some data that Fraunhofer IST gathered for us. And you can see, looking at the ion energies, I'd mentioned that the ion energy for the DMPTS was much lower. So typically 5 to 20 electron volts. You see the energy histogram of the ions on the left and the electrons on the right, which hit the chamber wall or the substrate, which is adjacent to the source orifice at different snapshot times. So usually the lowest ion gun energy is maybe around 75 to 100 electron volts, but more commonly higher than this, maybe 150 to 250 electron volts. And this can be pretty damaging to the substrate, whereas we're running at 5 to 20 electron volts and still able to treat the substrate efficiently. We looked at uniformity tests because when you're treating the substrate, you want to make sure that you're treating it uniformly, the whole substrate gets treated. So we did contact angle tests. You can see the picture on the left, the contact angle is 67 degrees, so the substrate is much more hydrophobic, and that was before pre-treatment. And then after treatment, the contact angle went down to 35 degrees. And next slide. And here's a graph just to show that. So you can see along the x-axis, the position along the DMPTS, which is equivalent to the position along the substrate, and then the contact angle on the left. So this is just after one pass, and you can see the red line is the untreated substrate, and then the measurements that we took on the treated substrate. You've got the top of the substrate on the left and the bottom of the substrate on the right, so you can see that the contact angle decreased all along pretty uniformly. Then we looked at surface energy testing. So these are the parameters that we use. The source to substrate distance was around 82 millimeters. The substrate velocity 6.7 meters a minute. We just did one pass, and I mentioned that higher power for the short duty cycle. The argon flow was 900 SCCM and oxygen 300 SCCM. Power supply voltage 490 volts, and the current 14.3 amps with a pressure of 10 millitorr. And this was the surface energy results that we looked at, that we achieved, with Accudine testing. So we had dyne pens, and the picture on the left shows the PET sample before pre-treatment. The top was at 44 dynes and didn't wet, and then the bottom was at 42 dynes that does wet. And then there's a picture on the right, the PET sample after pre-treatment, where you can see, so the limit of the test of the test pen was actually 60 dynes, so we know that we achieved at least 60 dynes or more, and that was along the length of a 650 millimeter substrate. Then we did further testing where we were looking at increasing the surface energy and then coating afterwards. So we did a slightly larger source to substrate distance of 100 millimeters. The substrate velocity was the same. The power was between 2 and 5 kilowatts. Argon flow, oxygen flow the same. And then the aluminum target power was around 4 kilowatts. We used a rotary aluminum target in the same chamber. Power supply voltage and the process pressure were the same too. So here I've got three graphs showing some results. This was for the first graph here, you can see was plasma pretreatment of polyethylene. You've got the treatment exposure on the x-axis and the surface energy on the y-axis, and adhesion on the y-axis too. So the blue line is the surface energy and the red line is the sputtered aluminum adhesion. So you can see with increased exposure time, the aluminum adhered much better to the film. And there was no observable overtreatment. We've mentioned that most sources can produce particles with high energy, and we didn't observe any treatment here, and the adhesion didn't drop off with significantly higher exposure. Then we looked at polycarbonate. So this graph's for the pre-treatment of polycarbonate, the same X and Y axis here. And with polycarbonate, it really required a significant amount of pre-treatment before the aluminum starts to adhere. But we were able to see that, you can see the treatment exposure here was much more than with the polyethylene. So we ended up doing 2 passes at 1 meter a minute and 5 kilowatts per meter. I should mention actually before this that we also did some tests on PET films, and we did demonstrate that we increased the surface energy. However, the aluminum already adhered well to the film before that, so that's just the nature of the PET film. But we still were able to see that we increased the surface energy with the measurements that we took. And then this is some results from a third-party testing. They used planarized plastic substrates and had 100 samples for each substrate type, so it was a nice sample field for us. They were running at 0.5 meters a minute and 1.85 millitorr, and used 100 millimeter source to substrate distance. And you can see that the surface energy and the adhesion in all cases had increased. So that was also a nice result for us. And I wanted to show you just an example. This is our partner, our distributor in Germany, Robeco, and this was an installation here. So I just had a real life example for you there. And you can see that they were actually doing some copper coatings afterwards. So they were treating a film and then they were doing copper coatings. So in conclusion, we showed the DMPTS source can increase the surface energy of plastic materials at low exposure rates. Some materials, such as polycarbonate, as we saw in that last graph, require treatment beyond the highest measurable surface energy for adhesion. And at low power levels, the source can effectively treat the whole substrate when the substrate is the same length as the beam aperture. Typically for magnetron sputtering, the target has to be significantly longer than the substrate to achieve the uniformity. But for this DMPTS, we found that if the substrate is the same length as the beam aperture, it's still able to achieve uniform treatment. So that was also a good result. The adhesion was improved on bare plastic substrates as well on substrates with planarization layers. So if you have any questions on that, then please, as I said, ask them in the Q&A box, and we'll get to them at the end of the webinar, hopefully. So now we'll move on to the CC cathode. We'll just introduce this briefly. So look at the basics here. It's a small, compact internal mount cathode for 80mm ID targets. We do other M blocks for 125mm ID targets, and this one specifically for 80mm ID targets. It can be run at 20 kilowatts DC or medium frequency AC power, 1500 volts, 50 amps. Maximum target length you can use this M block is around 1 meter, 1000 millimeters. If you want to go larger than that, then we would suggest that you would look at using our MC or SC cathodes if you're going much larger. And it's adaptable to user needs. We can configure that to what you require. I mentioned the spec sheet. So if you go to the resources, you're able to find the spec sheet, and you'll find the dimensions of this M block in there for you to be able to plan. So here is our family of N blocks, categorized by power rating. You can see the CC that we're going to talk about is here. Then we have the CMC, which is a compact MC, MC running up to 100 kilowatts, and then the SC usually in glass coating applications, large area glass coating applications up to 200 kilowatts. So along the top here is our family of internal mount, and then along the bottom is our family of external mount. So basically sisters. The CC would be a sister of the CM. Actually, the CM can also do 125 ID targets. Then you've got the MM and the SM. So what would this N block typically be used for? So usually for small coaters, for automotive components or tool coating, semiconductor applications, R&D coaters due to the small form factor, and also due to the small form factor, it's designed can be designed to replace planar cathodes in existing systems too. So definitely for smaller applications. This slide shows configuration. So you can see that the M block would be here, and then the utilities, the power and water, the motor and everything is here at atmosphere. And as with all of our M blocks, everything is just at the one end, the power, the water, all the utilities at the one end, and then it would be just a simple outboard support here. You can see the picture of the outboard support there too. And this is an example mounted in a process door. This would be to replace a planar. We could put 2 of these smaller rotary CC M blocks in there. And then we'll move on to look at the connections. So here, actually, many of the parts of the CCM block are common to the CC. Yep, are common to the CMN block too. So the same seals and the same bearings. Here on number 1, you see the water inlet and outlet. Number 2, the power cable attachment. You would just attach the power cable with a lug. The 3 is our encoder output signal to verify target rotation. All of our M blocks have that. And then 4 is a drip line port, so that you could use that for seal monitoring to decide when you're going to change your seals. 5 is a differential pumping port. If you wanted to monitor vacuum pressure, etc., or vacuum between the seals, you could do with that port there. And then it's a DC drive motor. So it's a DC drive because typically, rather than a VFD that we would use on our larger M blocks, just simply because it would be a smaller, lighter target and not as much torque as required. So why is a CC better than using a planar system? Points that I've put down here really are common to all rotary cathodes when you're comparing to a planar cathode, mainly the higher target utilization, 70 to 85% you'll get versus 25 to 40% for a planar, which will be especially important if you're looking at high value targets, precious materials, or some ceramic targets. There's reduced process drift. The stronger magnetic field design in a rotary cathode and a narrower design too compared to a planar cathode lowers the impedance and lowers the process drift. You also get less arcing and particle generation, simply because the target is moving all the time, so it's staying clean, so it doesn't arc as much. For rotary cathodes, there are 3 to 4 times the material available compared to planar cathodes, so you get much longer campaign times just purely because of the amount of material. And then due to less redeposition at the ends and the target constantly moving, when you're conditioning your target, it will take much less time than it would for a planar target. You also get high deposition rates, and that's because there's more efficient target cooling, higher volume of water is going through there, there's the lower impedance, and it just means that you can allow higher powers, which equate to higher rates. So, yeah, we'll keep your coater running. I mentioned it's a robust design. All of our M blocks are robust, simple designs. The water power rotation is on the one end, and the other end is a simple support. You saw that in the sketch. We have fewer than a third of the parts that you would usually find in a typical competitor rotary cathode. So it's also a simple design that works well. We have the most reliable power transfer that's patented. We use the same contact plate design in all of our M blocks, and as I said, that is patented. So, and even more importantly, they have a low cost of ownership. It takes around 30 minutes to replace the rotary seals. They probably need to replace them every 2 years. It takes around an hour to exchange the inexpensive wear parts. The seals, off-the-shelf seals, change every 4 years. It's designed for do-it-yourself maintenance. And online on our website, we have for all of our other M blocks, we have online instructional videos, and it shows you how to change the seals, the bearings, and other parts in there. For this M block right now, those videos are pending, but they will be up soon. We always supply a detailed manual. We can offer custom training. And for all of our M blocks, we have a special toolkit that makes the maintenance much easier as well. They'll have a vacuum seal tool, a water seal tool, and those kits are available to you as well. So is the CC right for your system? Then if so, we'd love you to contact us to work through the details. And thanks for your attention. If you have any questions, then I'll have a look in the Q&A right now to see if there are any, but otherwise you can send me an email. My email's right there, sarahw@sputteringcomponents.com, and my cell phone. And I hope that everybody's doing well and stays safe and healthy, and look forward to meeting you maybe someday in the not too distant future when we're through this. So thank you again. And I'm just going to look at the Q&A here. Okay. So we have a question: do the CC80 and the CM80 use the same type of magnet bar as the larger SCIM blocks? We can use actually we have some different types of magnet bars. The TRM80 and the SRM80 are what we would have to use for the CC80. So it is still a TRM design. So yes, we can use the same type of magnet bar. Do we have any data on plasma density, current density, any Faraday cup measurements? I would have to get back to you on that question. So I'll get back in the next couple of days. I'm not sure if we have data on plasma density, if that's specifically for the DNPTS, I assume. What gases have you tried so far? We tried oxygen and nitrogen for the DNPTS. And you mentioned the DNPTS uses titanium electrodes. Why was this material chosen? Have you looked at other materials like carbon for the electrode? We used titanium electrodes because of its low contamination rate. And I think if we looked at using carbon, we might get more contamination. So we haven't looked at specifically at other materials because the titanium electrodes worked so well. Yeah, so has the DMPTS testing ever been done on a glass substrate? We have done testing on glass substrates, but just for nickel coating. And we were trying to deposit quite thick nickel coatings, and we weren't able to do that. So we treated with the DMPTS, and we found that the treatment improved the nickel adhesion, but we've only done it with that so far. What's the typical maintenance time for DMPTS? So I think we went through that. Around 30 minutes to an hour would be to change out the shield and the electrodes. And one more. Net deposition on substrates of titanium when used as electrodes in the DMPTS. We haven't actually studied that. We know the deposition on the contamination is low, but actually we should add that to our next R&D tests. Oops. I think no more questions, and we're just about out of time anyway. So if there are any more questions, then please do send them to me, and I hope everyone has a nice afternoon, evening, morning, day. Thank you.